Very well. So, welcome everyone again to our penultimate session of the cryptography track on the Protocol Studies 2026. It's our second to last week. So, right after holidays, right after ETC. Thank you so much, so many of you joining us today. I think we have 18 people here. Great place to start, and we can pick up where we left off with the FFT and finally looking into the ECC crypto. Matan, go ahead.
Thank you, Mario, and welcome back. Those of you who made it, it's Easter and so on. But we decided to have the session nevertheless. We have two more planned sessions, this one and the next one. Last time we talked about FFT, and the key point of the whole algorithm, if you want to take something out of it, was that in appropriate extension field, you can find all roots of unity. So all the roots of the polynomial x to the n minus 1 for any n. I mean, for any small n, there will be a big N such that this polynomial has all roots. And this is what made the whole algorithm works. Without it, we didn't have any chance of getting the algorithm in the complexity time that we wanted. But I do realize that it can be hard to digest from where you stand. At least that's the feeling I got from the last session. It was a little bit of a didactic bet because technically all the material presented there, almost all, was covered in the previous sessions. But maybe it requires a certain amount of maturity, and maybe the intensity was a bit too much. And I got the feeling, at least, that you were struggling. And the plan for today was talk about elliptic curves, but instead of bombarding you with more mathematics, I want to dedicate this session to cryptography, very elementary cryptographic schemes that I hope would be first more easy to digest, and second, give you a motivation to keep on with the mathematics. So the first thing I want to talk about is what is called Shamir secret sharing. And I like to remind you that I like as many questions as possible. So feel free to write in the chat or to speak up. The idea, okay, so the motivation, suppose a nuclear launch requires authorization of 3 out of 5 people. So we want to encode the launch code. So that 3 or more can reconstruct it. But 2 or less cannot. And more abstractly, we have, this is called a threshold secret sharing. So n people a threshold t. T is, let's say, less or equal to n. So we have a secret, and the naive attempt, the secret S, well, divided into n pieces. So divide the secret S to n pieces and distribute among the n people. Well, then we don't satisfy the threshold because T people cannot reconstruct it. And and in fact, we really need to do it to the whole. I mean, only the whole group of n people can do it. So the scheme that actually does achieve it, I choose the parameters. I choose P bigger. In fact, it can be just any prime bigger than n. And T some threshold smaller than n, smaller or equal to n. And I encode my secret into FP. That's usually not a problem because, again, we can choose a very large prime, say 256-bit, and then you have a very big space to encode a secret. And the dealer samples A1 up to A t minus 1 uniformly at random. So this notation is uniformly at random elements from FP. And defines a polynomial. Fx is S, the secret, plus sum ai x to the I runs from 1 to t minus 1. This is a polynomial over the field Fp of degree exactly t minus 1. And then party I receives share Si which is simply f evaluated at I. I runs from 1 to n. Okay, so this is the sharing. And now, how do I reconstruct? Anybody has an idea? How do I reconstruct the secret if I have some T people out of the N people? Yes. So okay. So what do I do? Reconstruct. Given any set of people, so 1 up to n, we denote the people with the integers, of size exactly t. It could be more, but then I just take a t out of them. We are guaranteed, I mean, these guys, we have I S I for I, any index in the set S. So this is a set, what we called in the FFT lecture, we called a sampling representation. A sampling representation of size t. And hence, by Lagrange interpolation, there is a unique polynomial of degree t minus 1 or less. There exists a unique polynomial of degree less or equal to t minus 1, such that f of I is equal to s of I. So this polynomial, it has to be f. Yes, let's write it f bar. So in fact, f bar as a polynomial has to be equal to f. Then we have f. So then we get the secret by evaluating the polynomial at 0. Okay, so yes, questions. I see a question that says, is it guaranteed that a t minus 1 element will generate a polynomial of t minus 1 degree and not less? If you want, I mean, this is the probability. You can say that you take all the elements from fp minus 0. But in fact, for p large, if you sample randomly an element out of fp, the chance that it will be 0 is astronomically small. Okay, so for our primes, let's say p is about 2 to the 56, 2 to the 256. For example, then the chance that you get one of the AIs to be 0 in a random sampling is essentially 0. But you can really force it in the scheme by saying, and once all the coefficients AI are non-zero, then you're guaranteed to get a polynomial of degree exactly t minus 1. Other questions? Okay, so the next thing is a little bit of mathematics, but it's very much related to cryptography. The problem is there a cyclic group G? I write G multiplicatively, so it's something like this. And it's cyclic, but I want such that every non-unit element is a generator. Remember that one of the in the key exchange scheme that we talked about, the Diffie-Hellman key exchange, one of the setups was to choose a generator for a cyclic group, and we saw so non-example. FP star is a cyclic group, but it's not generated by any element. There are elements that will not generate at FP star. I cannot prove it so quickly, or actually maybe I could, but let me just let's accept this for now. What happens? I mean, if so I look at the order of the group. If the order of the group is not a prime, so it can be factor we could take I mean, it is a cyclic group, so it has a generator. G, and then I take the subgroup of G, H, generated by powers of G to the K. So in fact, the first one will be G to the K to the 0, G to the K to the 1. This is G to the K. This is 1. Then I have G to the K square, which is G to the 2K. And I run up until when? Up until I get to G to the LK, but G to the LK is equal to G to the N, and G to the N is 1. So this is 1. So H is a subgroup. H, if you want, the notation for this is the subgroup generated by the element G to the K. So you take all the powers of G to the K, and H is indeed a subgroup of G, but the size of H is well, actually it doesn't matter what the size of H. We see that H is not the entire group G, and so G to the K is not a generator. And in fact, it turns out that it's not so. So, for example, FP star, the size of FP star is P minus 1, right? Because I just removed the 0 element. P minus 1 is not a prime unless P is equal to 3. So, what typically will happen is that FP star will not be a group that is generated by any non-unit element. And in fact, it's not so easy to find a generator to FP star. So we want a group that every non-unit element of it will be a generator. For example, so that the setups in our schemes will be easier. And we see that we need to have a group of prime order. A group of prime order, and of course, well, we have a group of prime order, integers modulo p. But integers modulo p is not good because the discrete log is very easy. Integers modulo p with plus, and the discrete log is trivial. So I achieved my previous goal, but I'm not happy. So we want some kind of multiplicative group usually, but in fact, so we want a group in which the discrete log is hard, but is still of prime order. So now we did say that the discrete log in FP star, or FP star is like just integers modulo p when you remove the 0 and you take a multiplication modulo p and the unit element, right? This is FP star. And we did say last time, or the one before that, that it is assumed that a discrete logarithm in this group is hard. So what I want to, but this is not a group of order p. I want to maybe look for a group that sits inside this group and is of prime order. It's not going to be of order p because this whole thing is of order p minus 1, but maybe there is another prime that divides p minus 1, and I can find a subgroup of size exactly that prime. So this is the business of safe primes. P is called safe if so prime P, if there exists prime Q such that P is equal to 2Q plus 1. And we will soon see why we care about this. I mean, the idea is essentially the size here is P minus 1. So if P is a safe prime, then P minus 1 divided by 2 is Q. So maybe I can find a subgroup inside this creature that is exactly half of this size. Then it's easier to look. I mean, I need to find some principle that divides this set into two equal parts in a group manner. And then I will have a group of order Q. And so I need safe primes. Safe primes are conjectured to be to exist. I mean, it is conjectured that there exist infinitely many safe primes, but it's not known for sure. But for us, it doesn't matter in cryptography because all we need is that big enough safe primes exist. And safe primes, I think one of the biggest known is about 25K digits. So as you can imagine, it's well above any security bits of security requirements that we will want. So in practical purposes, it's good enough. But then the question is how to find a principle that divides this group FP star into exactly two halves. So this is the issue of a quadratic residues. And before I go to it, any questions about this? Okay, so and let P be a safe prime. Element A in FP star is a quadratic residue if there exists some x in FP star such that A is equal to x squared. Of course, in FP star, so modulo P. That's the reason for the name residue. And all quadratic, so these quadratic residues, they are denoted as, abbreviated for QR, and all quadratic residues are denoted QR sub P. And this, of course, is a subset of FP star. And the first thing to observe is that quadratic residues are in fact a subgroup. We denote subgroups by this small equal sign. And why is this true? Well, I need to show you two things. Well, three things. One is that the unit element is a quadratic residue, but that is clear. 1 is equal to 1 square. So 1 belongs to QRP. Then I need to show you that if I multiply two elements in QRP, I still get an element in QRP. So if A and B are quadratic residues, and say A is x squared and B is y squared, mod P. Then if I multiply them, A times B, well, that's x squared times y squared, mod P, but I can rearrange it to be x times y squared, mod P. So AB is also a square of something, so it's a quadratic residue. And A3, I need to show that if A is a quadratic residue, then the inverse of A is also a quadratic residue. But if A is equal to x squared, then A minus 1 is equal to x minus 1 squared. Or let me say, to x squared minus 1, which is the same as x minus 1 squared. So if A is a square of something, then also the inverse of A is a square of something. And we have shown that quadratic residues are, in fact, a subgroup of integers modulo P, or the multiplicative group of integers modulo P. Okay, and now I claim that QRP is a cyclic group of order Q. Q is P minus 1 divided by 2. So okay. So step 1, consider, remember we talked about homomorphisms. Group homomorphism. Let's call it phi, small phi, from fp star to fp star, which takes an element x and send it to x squared. Right? So this notation really says phi of x is x squared. Of course, modulo P. Now, of course, the image of phi, which is the set of all y in fp star, such that there exists x such that phi of x is equal to y. So basically, the collection of all outputs that you can obtain by applying phi. This is, by definition, the quadratic residues. Okay, and I claim that phi is a 2 to 1. Why is that? If x squared is equal to a, then, and that's actually an if and only if, minus x squared is also equal to a, of course, modulo P. So we see that we have two elements here, x and minus x, that are mapped to the same guy. Basically, phi of x is equal to phi of minus x. Okay, so we have exactly two elements that are mapped into one element, and I claim that there cannot be any other. Why? If y squared is equal to x squared mod p, then I do x squared minus y squared equal to 0. And this I break down to x minus y, x plus y equal to 0 mod p. So x is equal, has to be equal to plus minus y. Okay, so there is no other element y that is mapped to the same. I mean, apart from minus x, if y is different than x and minus x, then y is mapped into a different element. Okay, so so if this map is 2 to 1, then we know that QRP is of the size p minus 1 divided by 2, which is q. Now, why is it a cyclic group? This is basically a general feature. If you have a group of prime order, it has to be a cyclic group, because if it is not a cyclic group, then I take, so if QRP is not cyclic, say I just need one element, there exists X in QRP such that a QRP is not equal to what is generated from X. Then age equals the subgroup generated by X is a proper subgroup of QRP, and let's say X is not the unit element, and by Lagrange, the order of age must divide the order of QRP. But the order of QRP is prime, so there cannot be any subgroup age that is not that is of size bigger than 1 of QRP. So in fact, and that's a contradiction. So for any x in QRP, we have a QRP x different than 1. QRP is generated by x. Okay, so that's a little bit mathematics related to cryptography. Any questions on these quadratic residues? It's actually a very useful piece that appears in crypto. And okay, so the next thing I want to talk about, again, this is an eclectic collection of math and crypto, hopefully easily digestible. The next thing is hash functions. So, I mean, I guess you all heard about a hash function, but what do I really mean? A hash function is a function from 0, 1 star This is the notation for arbitrary length strings of bits, bit strings usually. So, you can have 0, 1, 1, 0, 1, 1, 0. That's a legitimate element. But you could also have 0, 1, 1, 1, 1. Okay, and you can choose any finite length. So a hash function is a function that takes an arbitrary length bit string and send it to 0, 1 to the lambda, where lambda is usually the notation for the security parameter. And we often take a lambda to be 256, but in fact it's open, right? And what we want from a hash function is three properties. One is that it's easy to compute. Maybe we call it 0, because that is really a practical property we want. So we want the hash function to be easy to compute. So easy to compute, say hx. Then we want that it's going to be hard to invert. Given hx, hard to recover x. But what do I mean hard? I mean, look, this is a set of infinite size. Or even if you restrict, usually you take bit strings of very large length, much larger than lambda, then because this set is much bigger than this set, there have to be some collision, okay? So in theory, by the pigeonholes principles, or the stuff we talked about with the injective and surjective maps, there has to be at least two elements, but in fact much more than two elements that are mapped to the same output. But we want the property that it's going to be a collision resistant, is hard to find two bit strings x and y such that age of x is equal to age of y. Now, what does it mean hard to find? Well, we want that in polynomial time with respect to the security parameter, an adversary cannot find a collision, even though collisions exist. I mean, just think of it. This set, the number of possible outputs is huge. I mean, this is, let's say, 2 to the 256. It's much more than the number of atoms in the universe, and so it's not going to be so easy. You cannot simply go over the entire space. nevertheless, there, I guess, you can make at least two types of hash functions. One hash function you can construct assuming some hardness assumption like the discrete log. And you will get a hash function that satisfy conditions 2 and 3, but is maybe not so, sorry, conditions 1 and 2, but maybe it's not so easy to compute. So what people do in practice is that instead of relying on hardness assumptions, they simply construct something that is seemingly very hard to invert and to find collision, but it is not relying on any hardness assumption. The only security guarantee you have is that this hash function exists and competitions are open to anyone and with good rewards. And anyone who finds an inversion or a collision resistance is rewarded. So if you know enough competitions have been held, this is your kind of security guarantee. But hash functions have been broken. So the first SHA-256 was broken. More recently, Poseidon 2 was broken. So this was a function that a hash function that people really relied on in constructing cryptographic schemes. And it's not the only thing that can be relied on, but it was broken. So be careful with hash functions, but of course, if you choose the right one, or you choose something that exists many years in a cryptographic usage, you should be safe. And what you can do with hash functions, and this exists in the Ethereum protocol, is well, you know what? We have some 10 minutes, so let me describe basically the most common attack on hash functions, and this relies on what is called the birthday paradox. So the question is, how many students need to be in a room such that the probability that there exist two students with the same birthday is let's say bigger than 50%. So the naive answer, you say, okay, I do 365 divided by 2, that's approximately 183. So if I have 183 students in a room, then I expect to have a collision of birthdays. But in fact, that's very far from the truth, and that's the reason that this is called the paradox, maybe here. Quotes are in place. Let's calculate the probability of no collision. What is this? Well, I let the first student get in the room, and I ask him his birthday, and by that there is in probability 1, I don't have any collision. Then the second students get in the room, and I ask him his birthday, and what I need to have is that his birthday is just not the same as the first one. The probability of this is 364 divided by 365. And I keep doing it. I mean, the third student, he needs to avoid 2 birthdays. So 363 divided by 365. And so on, until I get to the last student. So this is 365 minus n minus 1 divided by 365. This is the probability, I mean, the probability that there is no collision. It's like if all these events happened, the first student got in the room, the second student got in the room, and his birthday did not collide with the first. The third got into the room, and his birthday did not collide with the previous 2, and so on until the last student. So I need to evaluate this expression. This expression, I write it shortly as pi 365 minus I divided by 365. And I runs from 0 up to n minus 1. And let me write it slightly differently. This is 1 minus I divided by 365. I equal to 0, from 0 to n minus 1. And now I use some approximation for x smaller than 1. 1 minus x behaves very similar to e to the x, sorry, e to the minus x. And again, I mean, I'm leaving out the precise calculation of the error. But what we have is, I mean, so now I have let's call this guy x. This is smaller than 1, so I can replace this expression with e to the minus I over 365. And when I do that, what I get, so this is approximately pi of e to the minus I over 365, where I runs from 0 to n minus 1. And e of, I mean, product of exponents is exponent of the sum of the exponentials. So this is precisely e to the sum I equals 0 to n minus 1 divided by 365, and then minus here. Now, the sum of I when I runs from 0 to n minus 1 is approximately n squared. So this is approximately e to the minus n squared divided by 365. And and now I have a very compact expression. So now this is the probability of non-collusion, which n such that which n do I have such that e to the minus n squared divided by 365 is equal to exactly half. What's the kind of the break even? And the break even, oh, I forgot, this needs to be 365 times 2. So this is, I mean, the sum of I, where I runs from 0 to n minus 1, is about n squared divided by 2. So this is 2 to the 365. And I ask, when does it equal to half? Well, okay, I take ln, so I get a minus n squared divided by 2 times 365 is equal to ln half, and I reorder, and I get that n is equal to square root of 2 ln 2 times square root of 365, which is approximately 23. And this is the reason that this is called a paradox, because it's very, very far from the naive or intuitive answer. It's enough to have 23 students in the classroom so that in high probability we will have a collusion. Now, why do I say it? Because I want to apply the birthday paradox to the study of hash functions. Well, in hash functions, well, what I can do, if you give me a hash function and I want to find a collision, what I can do is just sample a lot of, just apply the hash functions on a lot of inputs, and hope for the best. But this is kind of a brute force. But the birthday paradox tells me that after 2 to the lambda square, I mean square root of 2 to the lambda hashes, we will likely find collision. Well, okay, so then this 2 to the lambda, square root of 2 to the lambda is 2 to the lambda over 2. So if you give me lambda that is, I mean, if lambda is equal to, let's say, 160, 2 to the 80 hashes are in fact feasible to compute. So a hash function that give you 160 bits is considered insecure today. But of course, we typically use hash functions of 256 bits, and that is well above the birthday attack. Okay, time for a break, but before that, any questions on that?
Folks, feel free to speak up. I think it's been a lot again, but Martin, I think it was a great lesson today. I really appreciate the Shamir explanation because I've been using it just for hardware wallets, so it's great to actually understand it under the hood.
It says this lambda that has been used for the hash function, apart from being the security parameter, is also the fixed length of the output. Yes. Hash functions need to be of fixed output length, and the length of the output is I mean, the length of the output divided by 2, roughly speaking, is the security that you get. This is what is called the bits of security. So for a hash function of size 256, you get 256 divided by 2 bits of security. Okay? What you do with hash functions, especially in Ethereum, but this is a wider construction, is called Merkle trees. Instead of writing the formal definition with a lot of indices, I have a data set. Can you still hear me? I've
Yes,
lost.
all good. Yeah. Can you hear us?
But I need to reconnect, I think, from my computer.
Yeah, the tablet works well.
Yeah. Okay. And then the video is on. Okay, it was off. Yeah. So I have a data set, say D1 up to Dn, where just for convenience, n is a power of 2. So let's say 2 to the k. And I want to commit to this data set. Well, we will soon speak more formally what is a commitment, but for now, I want using hash functions. So of course, I can just take age of a di, and this is a commitment. I mean, if I'm the data owner of di, and I want to prove to you some verifier, I want to commit to you, so I send you age of di, and then later in the future, if I want to prove to you that indeed I hold the di, well, I just give you di, and you can compute age of di and see that it's the same as the age of as the commitment that I sent you to begin with. So this is a way to commit to one value. Hash functions, they commit to one value. But what if I want to have a commitment to a bigger data set? Well, what I can do is, and let's say n is equal to 4. So I put the hashes of the of my data points in the leaves, and then I construct the hash of D1 concatenated with a hash of D2. And I put it in a big box. And I do the same here. This is hash of D3 concatenated with hash of D4. And in the root, I have a hash of the two things. And this I call the root. And now I have a data structure, and whenever I want to, the root is visible to the verifier, and if I want to prove to you that, let's say, hash of D1 is indeed an element in the tree, let's say an account in Ethereum, then what I need to provide you, I mean, I give you hash of D1, and I give you hash of D2, and together you can calculate the next level. So if I give you also this green information, then you can calculate the root, and the root is yellow, so this is public. Hash of D1 I gave you, and the green stuff is what is called the Merkle proof. So using the green information, if I give you the yellow input, and the root is assumed to be public, using the green information, you can verify that age of D1 is indeed a leaf in the tree. And it is committed in the sense that, I mean, in the same sense that hash functions are a commitment. This is just a repeated application of hash functions. And so assuming that you cannot find a collision, you cannot invert hash, then, you know, if I gave you the green information pictured here, then you can be assured that age of D1 is indeed a leaf in the tree, or an account, and so on. So this is one a very common use of hash functions. In fact, if you think of Merkle trees, you can use Merkle trees not just as commitments, but also to construct hash functions. So let's say I had a hash function from 0, 1 to the k into 0, 1 to the lambda. Okay, and but I mean, a typical hash functions need to be valid for any bit, any size of bit string that you input into it. Well, okay, I mean, you can use a Merkle structure. I mean, if you give me a bit string, if x is now a bit string of size, let's say 2k, then I divide the bit string into two pieces of size k. I hash this, and I hash the concatenation. And using this trick, of course, you can extend the original hash function, which was only for bit strings of size k. You can extend it to any size of bit string. Okay, so Merkle is kind of is a very useful construction for many things. There are, if I'm not mistaken, the later SHA functions are using this trick, this Merkle trick in order to construct their hash functions. Of course, that's not the only component, but it is relevant in practice. Yeah. Okay. So the next thing I want to talk about is, I guess, signatures. And the basic idea is, so Alice wants to send Bob a message, transfer 1,000 ETH to Carol. Okay, and of course, if Bob is able to verify that Alice sent this message, then he will make the transfer. So what we want is some kind of digital analog of a signature. If Alice has signed the message, and this signing is not forgeable, then Bob will accept and make the transfer. But of course, in the digital world, unlike in the physical world, you can very easily copy stuff. So the signature has to be kind of tagged into the message. And so we want unforgeability that is only Alice with some private key can sign a message and be verified. I mean, assuming that Alice sends her public key, then Bob can verify using the public key and using the information of the signature, can verify that this was indeed signed by Alice. And if you think of it, when you log into a website via Google and so on, you're essentially using a signature. So this next one is called RSA signature. And what we do here is the following. We take some integer n, and I can look at integers modulo n, but what is called the multiplicative group of integers modulo n. That is the set of all integers modulo n, such that there exists a multiplicative inverse to x. Okay, now n is typically not a prime, but rather a product of prime. So this is unlike, I mean, we have talked about integers modulo p and then multiplicative group, but there every element has a multiplicative inverse. Simply because fp is a field. So zp star is equal to zp minus 0, but zn star for a non-prime n is smaller than just Zn when you remove the zero. It's significantly smaller. Nevertheless, I can consider it as a set. In fact, it is a group. So this is a group for very similar reasons to the ones that we talked about when we talked about let's say quadratic residues or integers modulo p multiplicative group. And so in RSA, I choose n equals p times q, where p and q are large primes. Say 2 to the 1,000. And the first claim here is that, well, the size of the multiplicative group of integers modulo n for such an n is in fact p minus 1 times q minus 1. And why is this? Well, you take in order to have a multiplicative inverse for an integer modulo n, to have a multiplicative inverse, what you need, a necessary and sufficient condition, is that this integer is coprime to the modulus. Okay, so let's count the elements that are not coprime to the modulus and remove them. So I start with integers modulo n. I have to remove 0. And now, what else do I have to remove? Well, p is obviously not coprime to n because p divides n. But also every multiple of p, so p, 2p up to q minus 1 p, these guys, they have to be removed because they divide n. They are not coprime to n. When I get to q times p is already n, so it's outside of integers modulo n. But the other thing I can do is, I mean, in order to find the guys that are not coprime to n, well, I can take q, 2q, up to p minus 1 times q. And these guys are also not coprime to n because n is equal to p times q. How many elements did I remove? So let's count. Here I removed 1. And here I removed q minus 1. And here I removed p minus 1. So the size of integers modulo n star is n minus 1 minus q minus 1 minus p minus 1. And this is pq minus p minus q plus 1. And if you just assemble the elements, you get p minus 1 times q minus 1. But of course, it is, I mean, assuming that the integer n is public, it is considered very hard to find p and q. And so also it's considered hard to find p minus 1 and q minus 1. Okay, so now I do a key generation. Choose E smaller than P minus 1, Q minus 1, such that the GCD of E and P minus 1 times Q minus 1 is in fact equal to 1. And there is a nice hack here in practice. You can choose. There is some E that works almost always. Say 2 to the 16 plus 1 works, and is inconvenient. So now you compute D, which is the multiplicative inverse of E modulo N. Modulo the multiplicative inverse of E modulo P minus 1 times Q minus 1. And you discard your secret information, PQ. And now the public key is simply N and E. And the private key, or secret key, is N and D. Okay, and now I want to sign a message using my secret key so that it is verifiable using the private key, using the public key. So signing. Given a message M in, again, we encode the messages as some multiplicative integer modulo N. I can do, let's say, the naive signing is sigma equals to M to the D modulo N. The non-naive signing, because there is attack on this kind of signing, is choose hash function that hashes elements, bit strings, into multiplicative group of integers modulo N. And modify sigma to be hash of M. I first hash my message, and then I raise it to the power of D modulo N. Okay, and now let's say I want to verify. So Bob wants to verify that the message M and the signature sigma was indeed obtained by Alice secret key. So all you have to do is you take Bob calculates sigma to the E and verify that sigma to the E verifies that sigma to the E is equal to M modulo N. And why does it work? Because assuming that Alice was an honest signer, sigma is equal to let's say H to the, so here maybe, yeah, the sigma is equal to M to the D, but D is the multiplicative inverse of E. So if you do sigma to the E, you get M to the D to the E, which is M to the D times E, which is M modulo N. So an honest signer can sign correctly, but of course, what I'm omitting here in all of the schemes I presented is a full formal security proof based on some hardness assumption. This is it's too theoretical for our mini lecture series, but you can look it up. It's not very hard to follow. The
Lee,
last thing,
question or
yeah.
Yes.
Yes.
The question is, if we use the Z star or Z multiplication, I'm wondering if this is like multiplicative group or it's star group we're using.
Sorry, say again.
Yeah, because you say your notation is like the group we are using is Z multiplicative group, but
Mhm.
you are saying we are talking about it, you say it's Z star, so I'm wondering which one it is.
Yeah, I call it a ZN star.
Yeah.
I mean, some people denote it with an actual star. Some people denote it with an X. It's there's a bit, but yeah, I simply mean integers modulo n, where you only take the integers modulo n that have a multiplicative inverse.
Yeah, multiplicative. Yes. Okay. Thanks a lot.
And but as a rule of thumb, in crypto, we are not going to use integers modulo n additively because the discrete log is trivial to break. You see, so we typically want a multiplicative structure modulo some integer, because then the discrete log is hard.
Okay, thanks a lot.
Now I see a question from Jamal. With Merkle tree, how feasible is it to change data from earlier leaves? Do Merkles rely on the fact that data once entered must not edit it again? No. So coming back to Merkle trees, you can decide that you want to change the value to age of D1 prime, but then you need to hash again a hash of D1 prime concatenated with the, so you need to have the, in order to update, you also need to have the siblings here and here, and you update all the way up to the root. You update the tree, all the path of the leaf that you want to update. And so this is this, using the information of all the siblings that appear in the path, and you update the root. So everybody would, and then, so this is the new data structure. So it is possible to update, but of course, it takes some effort. It takes some a Merkle update proof. Yes. So no, the integers modulo n, Lee, is not of the size p minus 1 times q minus 1, because n in the RSA signature, n is assumed to be p times q. So integers modulo n is of the size p times q. If you remove 0, so it's the size p times q minus 1. Still not p minus 1 times q minus 1.
Oh, yes. Thanks.
Okay, and the last scheme I want to talk about is a commitment scheme. So this is polynomial commitment. So a polynomial commitment, what is the idea? So Alice has a secret polynomial. Some f over a prime field. Of course, polynomial is just as we saw a lot when we talked about the FFT. I mean, it's essentially just a vector, right? A vector of elements in FP. So you can encode a lot of secrets in a vector of FP, especially if P is large. And suppose the degree of the polynomial of the secret polynomial is D. So Alice has this secret polynomial and wants to commit to it. What does it mean? So remember, hash function is your canonical example of a commitment. But in a hash function, you simply hash your data. That's your commitment. And in order to prove, you just give the actual data to the guy you're trying to convince. And that is and then they can hash it themselves and see that you committed in an earlier stage to the correct bit string. But here we have a different requirement. So Alice doesn't want, so the requirements one is that once Alice commits, so this is called binding. Once Alice commits, she cannot change. The second property is evaluation proof for a public A. Alice can prove that she knows how to calculate f of A without revealing f. Right? Remember, the hash function is a very primitive commitment in the sense that in order to convince the verifier in a later stage that I committed correctly, I really need to reveal my data. And we also want short commitment. What is short? A few elements in FP would be okay. Okay, so this scheme. fix the prime P and the degree D such that D is much smaller than P. That's always practically possible to make, because Alice has a secret polynomial of degree D. I can choose a very large prime. How's the commitment working? Alice chooses, Alice already chose a polynomial. So Bob samples a uniformly random element R from FP. And Alice responds f of R. Okay, so all Alice did is just taking the random element that Bob sent her, and this is the commitment, C, and evaluating the polynomial on the randomness that Bob picked. So later, Alice wants to prove to Bob that she has F. Or rather, she wants to prove to Bob that f of A is equal to B for some public A and B, without revealing F. Okay, so what she does, I mean, observe that FA is equal to B if and only if x minus A as a polynomial divides f of x minus B. And this only happens if and only if there exists a polynomial, a quotient, Qx, in Fpx, such that Fx minus B is equal to Qx times x minus A. And Alice can compute this polynomial Q. So Alice computes Qx by long division. And since pi, this is the proof, which is the quotient polynomial Q evaluated at the original randomness that Bob sent. Now, Bob needs to verify. Bob checks that f of R, which he received in the original commitment that he received from Alice, is f of R, minus B, B is public, is equal to QR. QR he received now as the proof, times R minus A. And the whole thing, I mean, if you look at it, you see this is just here is just substituting R in the equation here. So assuming that Alice was honest, she can, I mean, Bob can verify. Security. So again, I'm not going to do a full security reduction or proof, but what we want to know, so I mean, if Alice is honest, then we saw that Bob can verify that she indeed committed to to the polynomial she claimed to have. But can Alice cheat by committing to F, and later on, so and later opening with F prime. That is in the stage where A and B are public. She proves that F prime of A is equal to B. So what she needs to do is to find a polynomial F prime such that F of R is equal to F prime of R. But F prime needs to be different than F. And I claim that this is very, very hard. And the reason is what is called the Schwarz-Zippel lemma. The Schwarz-Zippel lemma is, I mean, it's kind of a triviality, but it's very important to notice this triviality. If I have a polynomial of degree D, then for any B, the probability that if I take some A in random from FP and I evaluate F on A, I get B is less or equal than D over P. Right? And the proof of the Schwarz-Zippel lemma is simply saying, I mean, F of X, I mean, if F of A is equal to B, F of A is equal to B, if and only if X minus A divides Fx minus B. I mean, namely, A is a root of F, but F is a polynomial of degree D, so it can only have D roots. So assuming D is much smaller than P, the probability is astronomically low. And the Schwarz-Zippel lemma is let's say the backbone of the security proof that the polynomial that Alice cannot cheat. So this polynomial commitment is indeed secure. One last thing that I wanted to mention, but I don't have time to show you how, but you can pick it up in the internet. This type of polynomial commitment can be aggregated. Okay, it's I mean, if Alice wants to commit to any finite set of polynomials, she can do it with one commitment. You can kind of aggregate everything into one commitment. That's a beautiful and a super efficient property, and we often look for this property in commitments. We also look for this property in signatures, but the signature scheme I introduced is not aggregatable. I mean, I cannot aggregate many signatures into one signature, the RSA signature. And I think this is a great motivation for what we're going to do next time, which is BLS signatures. So BLS signatures are signatures based on elliptic curves. And one of the best properties they have is they are super efficiently aggregatable. And so I hope this is enough of motivation for you to climb the small hill of next time mathematics of elliptic curves, and we will I think hopefully keep you satisfied at the end. Yeah, that's it, I guess, for today. Any questions?
Thank you so much. Folks, do you have any thoughts, any questions before we wrap it up? It's been 2 hours lesson again here. Lee has comments. Go ahead.
Yeah, I have a question about our commitment schemes, and it's a KZG commitment, but in practical, we need to use like DL. But why do I? It looks like from the whole proof, we don't need the DL here, right? But why do we need
What is DL?
discrete log?
Oh, yeah, we don't have any discrete log here, but this is not KZG commitment. KZG commitment is another version of polynomial commitments based on elliptic curves. And again, the very nice properties of elliptic curves make KZG commitment very efficiently aggregatable and so on. Give it a very nice properties. But this is a polynomial commitment without any elliptic curves. So it's like it's a baby version, if you will.
Yeah, but I mean, it's basically like the idea behind the KZG, right? So I'm wondering why in practical we don't use this version.
Well, okay. So this gets into the details that I cannot fully answer, but it revolves around the proving of the commitment, the size of the commitment, the proving time of the commitment. I mean, let's say after I committed, I want to reveal how fast can I prove my my claim in the revealing stage. How big is the commitment? I do a commitment to a polynomial. I mean, in case if my commitment size is just one elliptic curve point, that's very small. Here, okay, so this revolves around revealing or proving time of the commitment and the size of the commitment, all sorts of efficiencies that KZG has in a better form, let's say.
Thanks a lot.
Okay, so feel free, by the way, to gather questions for next time about previous sessions. and ask. I mean, I'm always open to it, and I think it can help others to understand the material better. And with that, next time we're gonna climb the hill of elliptic curves, and at the end introduce a signature scheme that is first very used in practice, and second I think has a pretty aesthetic properties. Yeah, thank you, and see you next time.
Thank you so much, Matan. That's great. Awesome, guys. And we will see you for the last session next week. And I would also like to invite you for the Wednesday talk on the lean from Justin Drake. So we will see you there on Wednesday, and once again with Matan next week. So thank you so much for today. It was great. Yeah. And you can, when you the Artemis just reached the distance record, you can remember that when the record was broken, you've been learning cryptography at the time. So you can recall the moment for today. Thank you so much, guys.